In January 2026, two of the most powerful observatories ever built stared at the same patch of ancient darkness and found something that should not exist. Buried in the deepest X-ray and infrared images ever taken, 66 galaxies were caught assembling into a colossal structure barely 1 billion years after the Big Bang. That is 1 to 2 billion years earlier than any model predicted such a thing could form. This was not another distant galaxy. This was an entire city of galaxies, already gathering, already heating gas to millions of degrees, already building the skeleton of what would become one of the largest objects in the universe. The question is no longer just why early galaxies exist. It is why they were already organizing. If you enjoy having your understanding of the universe completely rearranged, consider hitting that like button and subscribing. It genuinely helps this channel keep exploring the biggest questions in science. Now, settle in and get yourself comfortable. Let's begin. $13.8 billion years ago, the universe began in a state that no analogy can faithfully represent. There was no explosion in the way you imagine one, no outward blast ripping through a pre-existing void. There was no void. There was no space. There was only an almost incomprehensible density of energy, compressed so tightly that the entire observable universe, everything you have ever seen or could ever see, occupied a volume smaller than a single grain of sand. Then, it expanded. Not into something. As something, space itself stretched outward, carrying energy and the embryonic seeds of matter with it, cooling as it grew, transitioning through phases so extreme that the physics governing each one differs from the physics governing every human experience. Within the first fraction of a second, the four fundamental forces separated from what may have been a single unified force, gravity, became its own entity. The strong nuclear force locked into place. The electromagnetic and weak forces split apart. During this first heartbeat of existence, the universe underwent a phase of exponential expansion called inflation, stretching quantum-scale fluctuations in energy density to cosmic proportions. These fluctuations were minuscule, variations of roughly 1 part in 100,000, but they mattered more than almost anything else that would ever happen. They became the blueprint. Every galaxy, every cluster of galaxies, every vast, empty void between them, traces its ancestry to those tiny ripples frozen into the fabric of expanding space before the universe was a trillionth of a second old. Within the first 3 minutes, the cosmos cooled enough for protons and neutrons to fuse into the lightest atomic nuclei. Hydrogen, helium, trace amounts of lithium. This is primordial nucleosynthesis, and it determined the chemical starting point for everything that followed. The universe was roughly 75% hydrogen and 25% helium by mass, with almost nothing heavier. No carbon, no oxygen, no iron, no element that would one day build rocky planets or living organisms. Those would have to wait for stars. But stars were still a long way off. For the next 380,000 years, the universe remained a blinding fog. Matter and radiation were locked together in a plasma so dense and hot that photons could not travel more than a short distance before colliding with free electrons and scattering in random directions. Light existed, but it could not move freely. The universe was opaque. Then came recombination. As expansion cooled temperatures below roughly 3,000 degrees, electrons finally bonded with nuclei to form neutral atoms. The fog cleared. Photons broke free and streamed across the cosmos for the first time. That light is still traveling. We detect it today as the cosmic microwave background, a faint thermal glow arriving from every direction in the sky, carrying a snapshot of the universe when it was less than 0.003% of its current age. It is the oldest light we can observe, and its temperature uniformity, just 2.7 Kelvin with variations of millionths of a degree, tells us the early universe was remarkably smooth, almost featureless, almost the same everywhere. After recombination, the universe entered what cosmologists call the cosmic dark ages. No stars had formed, no galaxies existed, no light source of any kind punctuated the blackness. There was only an expanding ocean of neutral hydrogen and helium gas drifting through silence, gradually cooling toward absolute zero. This era lasted somewhere between 100 and 200 million years. Nothing glowed, nothing burned. If you could have stood in the universe at that moment, you would have seen nothing at all. Total, absolute darkness in every direction. The darkness was not merely visual, it was informational. Nothing was happening that produced any kind of detectable signal. No electromagnetic radiation of any wavelength was being generated by any process anywhere in the cosmos. The only energy present was the cooling afterglow of the Big Bang itself, steadily dimming as expansion stretched its wavelengths toward longer, less energetic forms. The cosmic microwave background, which at recombination glowed with the color of a hot ember, faded through orange to red to deep infrared and continued cooling toward the microwave frequencies at which we detect it today. The universe was cooling, darkening, and expanding in silence. It was the longest quiet period in cosmic history, and nothing in the physics of that era guaranteed that it would ever end. But gravity was already working beneath the surface. Those primordial density fluctuations, the tiny variations imprinted during inflation, were quietly growing. Regions fractionally denser than their surroundings pulled in a little more gas. That extra gas made them denser still, which increased their gravitational pull, which drew in more gas. The process fed on itself, but agonizingly slowly. Dark matter, which does not interact with light and therefore was not affected by the radiation fog before recombination, had a head start. It began clumping together earlier than ordinary matter, forming invisible gravitational scaffolding, dark matter halos, that would eventually attract hydrogen and helium gas into their gravitational wells. The growth of these halos was governed by a relentless but patient mathematics. A region 10% denser than its surroundings does not collapse immediately. It first slows its expansion relative to the cosmos around it, then halts, then begins contracting. The time required depends on the density contrast and the expansion rate of the universe. For the small fluctuations seeded by inflation, this process required tens of millions of years for the smallest halos and hundreds of millions for larger ones. There was no shortcut. Gravity operates at a finite speed, and the information that a dense region exists can only propagate outward at the speed of light. The universe's first structures had to grow from the ground up, one gravitational interaction at a time. Over tens of millions of years, the densest of these halos grew massive enough for their gas to collapse and reach the temperatures and pressures required for nuclear fusion. The first stars ignited, probably between 100 and 250 million years after the Big Bang. They were likely enormous, perhaps 50 to 300 times the mass of our Sun, blazing with ultraviolet radiation, intense enough to begin ionizing the surrounding neutral hydrogen. These were not stars like the ones that populate our galaxy today. They formed from pristine gas containing no heavy elements, which changed how the gas cooled and fragmented during collapse. Without heavy elements to radiate away energy efficiently at low temperatures, the gas could not fragment into small clumps. Instead, it collapsed into fewer, larger masses, producing stars of extraordinary size and luminosity. These first-generation stars burned fast and died young. A star 300 times the mass of our Sun exhausts its nuclear fuel in roughly 2 million years, compared to the 10 billion year lifespan of a star like ours. When these massive stars died, many of them ended in supernova explosions of extraordinary violence, events that briefly outshone entire galaxies and scattered the first heavy elements, carbon, oxygen, silicon, iron, into the surrounding gas. Some died as pair instability supernovae, a type of explosion so complete that no remnant is left behind, dispersing the star's entire mass back into the interstellar medium. Others collapsed directly into black holes, seeds that would eventually grow into the supermassive black holes found at the centers of galaxies today. Those heavy elements would be incorporated into the next generation of stars, and the next, gradually enriching the cosmos with the chemical complexity needed for planets and eventually life. After the first stars came the first galaxies, small, clumpy, irregular collections of stars and gas, nothing like the grand spirals we see in the nearby universe. These early galaxies were assembled from merging dark matter halos, each one bringing its own small collection of stars and gas into increasingly massive structures. The process was hierarchical. Small things built bigger things. Bigger things merged into even bigger things. Each step took time. because each step required gravitational interactions to play out across vast distances. This is the picture that emerged from decades of theoretical work and observational confirmation. The standard model of cosmology, lambda cold dark matter, or lambda CDM, describes a universe composed of roughly 68% dark energy, 27% cold dark matter, and 5% ordinary baryonic matter. It has been tested against the cosmic microwave background, the large-scale distribution of galaxies, the abundances of light elements, the expansion history of the universe, and the properties of galaxy clusters. It has passed every major test. It is not a guess. It is the most successful quantitative framework in the history of cosmology. Within lambda CDM, the first billion years follow a clear narrative. Structure grows gradually. The most massive galaxies do not appear until the universe is several billion years old. In the first 500 million years, you might find small protogalaxies with stellar masses of tens of millions of solar masses, faint and compact and still assembling. In the first billion years, some of those protogalaxies might have merged into recognizable galaxies with stellar masses of a few 100 million solar masses, but nothing exceptional, nothing that would strain the model. The early universe was supposed to be a quiet construction site, laying foundations, not raising skyscrapers. This is the framework that the James Webb Space Telescope was built to test. Webb launched on December 25, 2021, aboard an Ariane 5 rocket from Kourou, French Guiana. It travelled to the second Lagrange point, a gravitationally stable location roughly 1.5 million kilometers from Earth, where it orbits the Sun in lockstep with our planet, always keeping its enormous sun shield pointed toward the Sun, Earth, and Moon to maintain its instruments at temperatures near -230 degrees Celsius. Webb carries a primary mirror 6.5 meters in diameter, composed of 18 gold-coated hexagonal segments. Its collecting area is roughly 6 times that of Hubble, giving it the ability to gather light from objects so faint and so distant that no previous observatory could detect them. But the defining feature of Webb is not its size, it is its wavelength range. Webb is an infrared telescope optimized to observe light at wavelengths between 0.6 and 28 microns, far beyond what human eyes can perceive. This design choice was deliberate and essential for one reason: cosmic expansion stretches light. When a galaxy emits ultraviolet or visible light in the early universe, that light travels for billions of years through expanding space. During the journey, the wavelengths stretch. Ultraviolet becomes visible. Visible becomes near-infrared. Near-infrared becomes mid-infrared. By the time light from the most distant galaxies reaches Earth, it has been redshifted so dramatically that only an infrared telescope can capture it. Hubble, with its limited infrared sensitivity, could peer back to roughly 400 million years after the Big Bang, but only barely, catching the faintest smears of light at the edge of its capabilities. Webb was designed to see further, see more clearly, and see in the wavelengths where the earliest cosmic light now arrives. The telescope began full science operations in July 2022. Within weeks, the first deep field images arrived. Within months, the astronomical community realized that the early universe looked nothing like what lambda CDM had led them to expect. Galaxy after galaxy appeared at redshifts above 10, meaning their light was emitted when the universe was less than 500 million years old. Some were detected at redshifts of 11, 12, 13. These were not the faint, fragile proto-galaxies that models predicted for such early epochs. Many were surprisingly luminous. Their spectra, captured by Webb's near-infrared spectrograph, revealed emission lines from oxygen, neon, and other elements that should not have been present in significant quantities so soon after the Big Bang. These elements require multiple generations of stars to produce, stars that must live, die, scatter their enriched material into space, and then have that material incorporated into new stars. Each cycle takes millions of years. Finding chemically enriched galaxies at redshifts above 10 implied that star formation had been underway vigorously almost from the moment the first halos were massive enough to support it. Then came the discovery that crystallized the tension into something impossible to ignore. In early 2024, a team analyzing data from the JWST Advanced Deep Extragalactic Survey confirmed the spectroscopic redshift of an object designated JWST 14.0. The confirmed redshift was 14.32. Translate that number into cosmic time, and the result is staggering. The light from this galaxy was emitted just 290 million years after the Big Bang. The universe at that moment was roughly 2% of its current age. If you compress the entire history of the cosmos into a single calendar year, with the Big Bang at midnight on January 1st and the present moment at midnight on December 31st, this galaxy existed on January 8th, 8 days into a cosmic year, and yet Jade's JWST 14.0 was not a faint point of light. It extended across more than 1,600 light-years, large enough that its luminosity clearly originated from a substantial population of young stars rather than from a single accreting black hole. It had already assembled a meaningful stellar mass in a window of time so narrow that standard models could barely account for the dark matter halo existing, let alone the galaxy within it. The sheer physical extent of the object was itself a challenge. Galaxies do not spring into existence fully formed. They grow through the merger of smaller systems, each merger requiring gravitational interactions that unfold over millions of years. For a galaxy spanning more than 1,000 light-years to exist just 290 million years after the Big Bang implies a formation history that began astonishingly early, possibly within the first 100 million years, deep in the cosmic dark ages, when the standard model predicts only the tiniest dark matter halos should have existed. Jade's JWST 14.0 was not alone. Across every deep survey field Webb examined, a consistent pattern repeated. Galaxies appeared at redshifts of 10, 11, 12, 13, and beyond, brighter and more massive than predictions allowed. Some showed evidence of mature stellar populations, stars that had been burning long enough to evolve off the main sequence, at times when the universe was less than 400 million years old. Some contained dust, a material produced when heavy elements condense in the outer layers of dying stars, and in supernova ejecta, a material that requires previous generations of stars to create. The early universe was not merely populated, it was industrious, assembling complex structures at a pace that outstripped the most optimistic projections. The tension with lambda CDM came down to a problem of budget. In the standard model, the amount of ordinary matter that can collapse into stars within any given dark matter halo is limited. Feedback processes, supernova explosions that blow gas out of galaxies, radiation pressure from massive stars that heats surrounding gas and prevents it from collapsing, regulate star formation and keep it well below the theoretical maximum. Typical galaxies convert only a few % of their available baryonic matter into stars during any given period. For the galaxies Webb was detecting at the highest redshifts, the implied star formation efficiencies were far above typical values. In some cases, the inferred stellar masses suggested that galaxies had converted 30, 50, even close to 100% of their available baryons into stars, numbers that are extremely difficult to achieve under standard physics. The community responded with rigor and caution. Several lines of investigation sought to reduce the tension. Perhaps the stellar masses were being overestimated. Early photometric measurements, which infer galaxy properties from broadband colors rather than detailed spectra, carry significant uncertainties. An unusually top-heavy initial mass function, meaning the first galaxies produced a higher proportion of massive luminous stars, could make a galaxy appear brighter and more massive than it truly is. Active galactic nuclei, where matter falls into a supermassive black hole and releases enormous energy, could contribute additional light that gets mistaken for starlight, inflating mass estimates. Some initial candidates were indeed revised downward when spectroscopic data replaced photometric estimates. A few high-profile candidates turned out to be at lower redshifts than first reported or had their properties significantly adjusted. But the corrections did not eliminate the problem. They shaved its edges. Even after applying the most conservative assumptions, a substantial population of bright, massive galaxies persisted at redshifts above 10. Their abundance exceeded the predictions of lambda CDM simulations by factors that could not be dismissed as statistical noise. The issue was not a single anomalous object, it was a population, a pattern, a persistent discrepancy between observation and theory that demanded explanation. Several explanations remain on the table. As of 2026, one possibility is that star formation in the earliest galaxies was genuinely more efficient than in later cosmic epochs, driven by conditions unique to the early universe: higher gas densities, lower metallicities, reducing cooling radiation losses, the absence of magnetic fields that would later regulate collapse. Another possibility involves modifications to the cosmological model itself. Early dark energy, a hypothetical component that increases the expansion rate before recombination, has been shown in simulations to accelerate structure formation, producing more massive dark matter halos at high redshift and easing the tension with observed galaxy populations. A third possibility is that the initial density fluctuations from inflation contained more power on small scales than the standard model assumes, giving the first structures a slight gravitational head start that compounded over hundreds of millions of years. None of these explanations has achieved consensus. The debate is active, technically demanding, and far from resolution. What is universally agreed upon is the observation itself. The James Webb Space Telescope confirmed that the early universe assembled galaxies faster, brighter, and more chemically complex than anyone expected. The first billion years were not a gentle awakening. They were an eruption of structure formation that caught the theoretical community off guard. But while this debate consumed the attention of the astronomical world, something even more troubling was emerging from the same Webb data. Something that escalated the crisis from surprising to genuinely unsettling. The early galaxies were not always alone. The realization did not arrive as a single announcement. It emerged gradually, as independent teams analyzing different survey fields began reporting the same anomaly. A group studying the JWST fields noticed that certain redshift bins contained suspiciously more galaxies than neighboring bins, suggesting concentrations in three-dimensional space rather than uniform distributions. A separate team examining the region behind the gravitational lens of Abell 2744 found multiple galaxies at identical redshifts, packed into volumes far too small for random chance. Others working with narrowband imaging surveys on ground-based telescopes flagged overdensities of Lyman alpha-emitting galaxies at redshifts above 6, concentrations that Webb's deeper imaging subsequently confirmed and expanded, with additional fainter members invisible to earlier instruments. At first, each team treated its own finding as a local curiosity, an interesting clustering that might reflect a filament of the cosmic web, or a modest overdensity that would be consistent with normal statistical variance. But as the reports accumulated across unrelated survey fields spanning different parts of the sky, analysed by different teams using different methods, the cumulative picture became impossible to dismiss as coincidence. The early universe was not merely producing galaxies ahead of schedule, it was producing them in groups. In field after field, survey after survey, astronomers found ancient galaxies clustered together, not randomly scattered across the sky like isolated streetlights, but grouped, concentrated in the same small volumes of space at the same cosmic epoch. Multiple galaxies at matching redshifts, sitting in the same neighborhood, moving at velocities that hinted at shared gravitational environments. This was not the signature of individual objects forming in isolation. This was the signature of something larger, something organized, galaxies already gathering into the embryonic stages of structures that in the nearby universe grow into the most massive, gravitationally bound objects that exist. Finding a single galaxy too early is a problem of star formation physics. It can be explained, at least in principle, by invoking unusual conditions inside one exceptional dark matter halo. Perhaps that halo was denser than average. Perhaps its gas cooled more efficiently. Perhaps its star formation was unusually vigorous due to a lack of feedback processes that had not yet had time to develop. These are local explanations. They require adjusting the physics inside one object, one halo, one galaxy. They are uncomfortable but manageable within the existing theoretical framework. Finding many galaxies already clustering together is a problem of a completely different magnitude. When dozens of galaxies appear at matching redshifts within the same compact volume of space, the explanation can no longer be local. You are no longer asking why one halo outperformed expectations. You are asking why an entire region of space developed enough gravitational contrast to begin pulling multiple halos together, each already hosting its own galaxy, within the first billion years. That is not a question about what happened inside one object. That is a question about the initial conditions of the universe itself, about how much density contrast the primordial fluctuations contained, about how rapidly gravity amplified that contrast into the cosmic web's earliest architecture. It means that the large-scale density field itself has already developed enough structure for gravity to operate on scales far larger than any individual galaxy. It means dark matter halos have not only formed but have found each other, begun merging, begun assembling the gravitational architecture that will eventually host galaxy clusters containing thousands of members and masses of quadrillions of solar masses. The question was no longer just how individual galaxies appeared so early. It was how the universe was already building something bigger. And the answer, when it came, arrived from the combined power of two observatories seeing the same patch of ancient sky in two completely different kinds of light. When you look at a photograph of the night sky taken through a powerful telescope, you see galaxies scattered across the frame like luminous dust. The instinct is to think of each galaxy as a separate, independent object floating through empty space. This instinct is wrong. Galaxies are not scattered randomly. They are organized into a vast, interconnected architecture that spans the entire observable universe, a structure so enormous and so precisely arranged that its existence encodes information about the physical conditions that prevailed when the universe was less than a second old. Understanding this architecture, and understanding why finding it forming so early is such a profound problem, requires starting from the foundations. The universe is not a uniform distribution of matter sprinkled evenly through space. If you could zoom out far enough, far beyond individual galaxies, far beyond even groups and clusters of galaxies, the cosmos would reveal itself as a network. Filaments of matter stretch across hundreds of millions of light years, connecting dense nodes where galaxies cluster together by the thousands. Between these filaments lie vast empty regions called cosmic voids, bubbles of near emptiness, sometimes hundreds of millions of light years across. The filaments form walls and sheets where they intersect, creating a foam-like geometry that cosmologists call the cosmic web. This web is not a metaphor. It is a directly observed, precisely mapped physical structure. Galaxy surveys like the Sloan Digital Sky Survey have charted millions of galaxies in 3 dimensions, revealing the web in stunning detail. The pattern is unmistakable. Matter concentrates along filaments. Filaments converge at nodes. Voids fill the spaces between. The entire observable universe is threaded through with this architecture, and it looks remarkably similar in every direction, confirming one of cosmology's foundational assumptions, that the universe, on sufficiently large scales, is roughly the same everywhere. The cosmic web exists because of gravity, and gravity alone. Those primordial density fluctuations, the tiny variations imprinted during inflation, provided the initial blueprint. Over billions of years, gravity amplified those variations. Regions slightly denser than average attracted more matter, grew denser still, and eventually collapsed into the structures we observe today. Regions slightly less dense than average lost matter to their denser neighbours and became voids. The process is deterministic in its broad strokes, meaning if you know the initial conditions and the laws of physics, you can predict the statistical properties of the resulting web. Computer simulations running lambda cold dark matter cosmology forward from the initial conditions observed in the cosmic microwave background produce webs that match the observed universe with remarkable fidelity. Within this web, structures exist at every scale, and they are arranged in a hierarchy. At the smallest cosmic scales are individual galaxies. A galaxy like the Milky Way contains roughly 400 billion stars, a central supermassive black hole, vast reservoirs of gas and dust, and an enormous halo of dark matter extending far beyond the visible disk. The Milky Way is a substantial object by any measure, but in the context of the cosmic web, it is a single point of light on a single filament. Galaxies group together. The Milky Way belongs to the local group, a collection of more than 50 galaxies gravitationally bound to one another, dominated by 2 large spirals, the Milky Way and Andromeda, accompanied by dozens of smaller dwarf companions. The local group spans roughly 10 million light-years. This is a galaxy group, the smallest unit of gravitationally bound multi-galaxy structure. Above galaxy groups sit galaxy clusters, and this is where the scale becomes genuinely difficult to comprehend. A galaxy cluster is not merely a bigger group, it is a fundamentally different kind of object. A typical massive cluster contains hundreds to thousands of individual galaxies, but the galaxies themselves account for only a small fraction of the cluster's total mass, roughly 3 to 5%. When astronomers first began studying galaxy clusters in the mid-20th century, they assumed the visible galaxies were the main event, the substance of the cluster. They were wrong. The galaxies are almost decorative. The dominant component by mass is dark matter, forming a halo so enormous that it bends the paths of light from background galaxies through gravitational lensing. Dark matter accounts for roughly 80 to 85% of a cluster's total mass, an invisible gravitational architecture that determines the cluster's shape, its depth, and the orbital velocities of everything within it. Without dark matter, galaxy clusters could not exist. The visible galaxies moved too fast to be held together by their own gravity alone. This was one of the earliest lines of evidence for dark matter's existence, identified by the astronomer Fritz Zwicky in the 1930s, when he noticed that galaxies in the Coma cluster were moving so rapidly that the cluster should have flown apart long ago unless it contained far more mass than its visible matter could provide. The second most massive component is hot gas, the intracluster medium, and this is the component that will become most important for our story. The intracluster medium is a vast atmosphere of ionized hydrogen and helium, heated to temperatures of tens of millions of degrees, sometimes exceeding 100 million degrees in the most massive clusters. At these temperatures, the gas is a fully ionized plasma, a state where atoms have been stripped of their electrons so completely that what remains is a seething broth of free protons, bare helium nuclei, and electrons moving at speeds comparable to a fraction of the speed of light. This plasma is so hot that it glows brightly in X-ray wavelengths, radiation far more energetic than visible light, radiation that ordinary optical telescopes cannot detect. Only X-ray observatories, instruments like Chandra or the European Space Agency's XMM Newton, can see this gas. The intracluster medium fills the space between cluster galaxies and contains more baryonic mass than all the cluster's galaxies combined. This is a fact that continually surprises people encountering it for the first time. The stars, the planets, the dust, the cold gas within every single galaxy in the cluster, add them all up and they are still outweighed by the hot, diffuse, X-ray glowing plasma that fills the space between them. The galaxies are bright. The gas is dim to human eyes but blazing in X-rays, and the gas contains more substance than all the galaxies put together. The galaxies are almost an afterthought, bright tracers embedded within a far more massive structure of dark matter and superheated plasma. This hot gas does not appear by accident. It is produced by gravity. As a galaxy cluster assembles over billions of years, matter flows inward along the filaments of the cosmic web. Gas from the surrounding intergalactic medium falls into the cluster's deep gravitational potential well, accelerating as it falls, gaining kinetic energy from the conversion of gravitational potential into motion. When this infalling gas collides with gas already present in the cluster, or with gas flowing in from other directions, the kinetic energy is converted into thermal energy through shock waves. These accretion shocks are the mechanism by which clusters heat their gas to extreme temperatures. The deeper the gravitational potential well, the faster the gas falls, and the hotter it gets upon impact. The most massive clusters have the deepest potential wells, producing the hottest gas and the brightest X-ray emission. This is why detecting hot gas in a cluster or protocluster is so significant. The presence of hot, X-ray-emitting gas is direct evidence that a gravitational potential, well deep enough to shock heat baryonic matter to millions of degrees, has already formed. It is the thermodynamic fingerprint of gravitational collapse on a massive scale. A massive galaxy cluster can have a total mass exceeding 1 quadrillion solar masses, or 10 to the 15th power solar masses. That is more than 1,000,000 billion times the mass of our Sun. The Coma cluster, one of the best studied examples, contains over 1,000 large galaxies and sits at the center of the Coma supercluster, roughly 320 million light-years from Earth. Galaxy clusters are the most massive gravitationally bound structures in the universe. Nothing larger has had time to fully collapse under its own gravity since the Big Bang. This is the critical distinction. Galaxy clusters represent the endpoints of gravitational collapse on the largest scales the universe currently allows. They sit at the nodes of the cosmic web, where multiple filaments converge, where matter has been funneling inward for billions of years, where gravity has had the longest and most powerful opportunity to pull structure together. They are the densest, most evolved concentrations of matter in existence, and their properties, their masses, their abundances, their distribution across cosmic time encode fundamental information about the laws governing structure formation. Above clusters, the hierarchy continues into superclusters, collections of clusters and groups linked by filaments but not necessarily gravitationally bound as single objects. Our local group belongs to the Laniakea supercluster, a gravitational basin spanning roughly 500 million light-years and containing more than 100,000 galaxies. But superclusters are loosely defined. They are not collapsed structures. They are regions of the cosmic web where density is enhanced, where matter flows toward common gravitational attractors, but where cosmic expansion still competes with gravity and may ultimately win. This hierarchy, from galaxies to groups to clusters to superclusters to the web itself, did not appear instantly. It grew, and it grew in a specific sequence, because gravity operates at a speed determined by the density of matter and the rate of cosmic expansion. In the standard model, the smallest dark matter halos collapsed first, because small-scale density fluctuations reached the threshold for gravitational collapse earliest. The first dark matter halos to form were tiny, far too small to host anything resembling a galaxy. Over hundreds of millions of years, these small halos merged into larger ones. Galaxies began forming inside the most massive halos. Galaxy groups assembled over the first few billion years as halos continued merging. Galaxy clusters, the largest collapsed structures, required the convergence of multiple groups and the accumulation of mass along cosmic web filaments, a process that models predicted would not produce recognizable clusters until at least 2 to 3 billion years after the Big Bang. Before that, there simply had not been enough time for gravity to pull sufficient mass together over the necessary volumes. The hierarchy had to be built from the bottom up, and the largest structures sit at the top, requiring the most time. This is where protoclusters enter the story. A protocluster is the precursor to a galaxy cluster. It is not yet a cluster. It has not yet collapsed into a single gravitationally bound system. Its galaxies are not yet embedded in a unified atmosphere of superheated gas. But it is a region of space where the density of galaxies and the density of dark matter significantly exceeds the cosmic average. It is a region where gravity is already winning, where matter is already flowing inward from the surrounding cosmic web, where the seeds of a future cluster are already planted and growing. Identifying a protocluster is substantially more difficult than identifying a mature cluster. A mature cluster announces itself through multiple unmistakable signatures. Its hot intracluster medium glows in X-rays. Its total mass bends light from background galaxies through gravitational lensing. Its member galaxies share a common redshift and show high-velocity dispersions, evidence of deep gravitational potential wells. A protocluster, by contrast, is subtler. Its galaxies are loosely distributed. Its gas, if heated at all, may not yet be hot enough or dense enough to produce detectable X-ray emission. Its gravitational lensing signal is weak. The primary way to identify a protocluster at high redshift is to find an overdensity of galaxies, a region where more galaxies exist at the same redshift than you would expect from a random distribution. Before the James Webb Space Telescope, finding such overdensities in the first billion years was an exercise in patience and frustration. Ground-based telescopes like the Subaru telescope on Mauna Kea in Hawaii and the Keck Observatory, among the largest optical and near-infrared instruments on Earth, could identify individual galaxies at high redshifts, but their sensitivity was limited. They could find the brightest galaxies, the rare luminous objects that stood out against the noise of the sky. What they could not do was systematically detect the populations of fainter galaxies that would reveal whether those bright objects were solitary or surrounded by companions. One bright galaxy at a redshift of 7 tells you almost nothing about whether it lives in a cosmic overdensity. You need to see its neighbours, and its neighbours are faint. Despite these limitations, the pre-Webb era produced tantalizing hints. In 2019, a team using Subaru, Keck and Gemini published two landmark discoveries from narrowband imaging surveys. The first was an overdensity designated Z57OD, a collection of 44 galaxies identified at a redshift of 5.7, corresponding to roughly 1 billion years after the Big Bang. The second was Z66OD, a smaller but even more distant overdensity containing 12 galaxies at a redshift of 6.6, corresponding to just 800 million years. These structures were identified through a clever technique: narrowband filters tuned to detect Lyman alpha emission, a specific wavelength of light produced by hydrogen gas illuminated by young stars. Galaxies emitting Lyman alpha at the same redshift within the same patch of sky were flagged as potential Protocluster members. These were the most distant Protocluster candidates ever identified at the time. Their existence was suggestive. 12 galaxies at a redshift of 6.6, concentrated in one patch of sky, implied that the cosmic density field already had enough contrast to produce meaningful overdensities within the first 800 million years. But the evidence remained incomplete. The galaxy counts relied partly on photometric redshifts, which carry significant uncertainties. Spectroscopic confirmation for many of the candidate members was lacking, and the masses and total halo properties of these overdensities could only be estimated indirectly, using statistical arguments about how likely such concentrations were to arise by chance. The structures were real enough to be published in major journals. They were not certain enough to conclusively demonstrate that cluster-scale assembly had begun. Hubble contributed as well, identifying possible overdensities of high redshift galaxies near bright or lensed objects. But Hubble's infrared capability was limited to a single, relatively narrow band, and its sensitivity at the longest wavelengths fell short of what was needed to reliably detect the faintest galaxies at redshifts above 6. The state of protocluster science before Webb can be summarized simply: we knew overdensities probably existed in the first billion years, we had a handful of candidates, but we lacked the tools to move from candidates to confirmed structures with characterized populations. Webb changed this equation completely. Its infrared sensitivity, its spectroscopic capabilities through the near-infrared spectrograph, and its deep imaging surveys allowed astronomers to detect not just the brightest galaxies in the early universe, but populations of fainter galaxies surrounding them. For the first time, astronomers could measure precise redshifts for multiple galaxies in the same field and determine whether they occupied the same volume of space. The results arrived quickly, and they were startling. In 2023, a team using Webb data confirmed the spectroscopic redshift of a protocluster behind the galaxy cluster Abell 2744. The protocluster existed at a redshift of 7.88, corresponding to just 650 million years after the Big Bang. 7 galaxies were confirmed within a projected radius of roughly 60 kiloparsecs, roughly 200,000 light-years. That is an extraordinarily small volume to contain 7 distinct galaxies at such an early epoch. To appreciate how unusual this is, consider that the average density of galaxies at this redshift is extremely low. The universe was still emerging from the cosmic dark ages. Most regions of space at this epoch contain no detectable galaxies at all within comparable volumes. Finding 7 in such close proximity was like discovering a small town in the middle of what every map insisted was uninhabited wilderness. The density of galaxies in this region exceeded the expected value for a random volume by a factor of more than 20. The galaxies showed high-velocity dispersions, roughly 1100 kilometers per second, suggesting they were embedded in a dark matter halo of considerable mass. These velocities are themselves significant. In the nearby universe, galaxy clusters typically show velocity dispersions of several hundred to over 1,000 kilometers per second, reflecting the depth of their gravitational potential wells. Finding similar velocities in a structure just 650 million years old suggests that a substantial dark matter halo had already assembled, one deep enough to accelerate its member galaxies to speeds far exceeding anything typical of isolated galaxies at this epoch. Using empirical relationships between halo mass at high redshift and the eventual mass of present-day structures, the team estimated that this protocluster would evolve into something comparable to the Coma cluster, one of the most massive galaxy clusters in the nearby universe, with a present-day halo mass of roughly 2 × 10⁻⁵ solar masses. The seed of a future giant was already planted in the first 700 million years of cosmic history. This was the highest redshift, spectroscopically confirmed protocluster ever observed. The universe had barely finished reionization, the process by which the first stars and galaxies ionized the neutral hydrogen filling intergalactic space. And already, in at least one location, galaxies had found each other and begun assembling into something larger. A subsequent study in 2025 examined the protocluster in even greater detail, finding that its core galaxies were remarkably evolved for their age, with chemical enrichment and star formation histories suggesting an unexpectedly mature environment. But this protocluster, as remarkable as it was, came with a significant caveat. It contained only 7 confirmed members. Its total inferred halo mass, while substantial for that epoch, was still modest compared to the massive protoclusters that form the progenitors of today's richest clusters. And critically, it showed no sign of one of the defining features of a forming cluster, hot gas. Meanwhile, a different kind of early structure was emerging from Webb data at a slightly later cosmic epoch. The cosmic vine, discovered in data from the Cosmic Evolution Early Release Science Survey, is a massive protocluster at a redshift of 3.44, corresponding to a time when the universe was roughly 2 billion years old. The vine is not a compact knot of galaxies like the Abell 2744 protocluster. It is a chain, a filamentary structure stretching more than 13 million light-years in length and roughly 650,000 light-years in width. To put that length in perspective, the Milky Way is roughly 100,000 light-years across. Line up 130 Milky Way galaxies end to end, and you would roughly span the length of the cosmic vine. It is an enormous object by any standard, dwarfing the typical protocluster structures found at similar redshifts. The initial discovery identified at least 20 closely packed galaxies within the vine. Subsequent studies using deeper Webb archival data expanded this census dramatically, confirming 136 spectroscopic members in the vine itself, plus 47 additional galaxies belonging to a diffuse foreground structure, the researchers named the leaf. 4 distinct subgroups were identified within the vine, each one a concentration of galaxies dense enough to represent a potential future cluster core. The vine is not a single collapsing entity, but a collection of overdensities strung along a cosmic web filament, each one in the early stages of assembly, connected by the gravitational highway of dark matter and gas flowing between them. The cosmic vine is significant for several reasons beyond its size. Among its confirmed members are 11 quiescent galaxies that have already stopped forming stars and are passively evolving. This is the largest sample of quiescent galaxies in an overdense environment at a redshift above 3. In the nearby universe, quiescent galaxies are overwhelmingly found in the densest environments, in the cores of rich galaxy clusters, where interactions with hot intracluster gas and frequent encounters with neighboring galaxies strip away star-forming fuel. The process is called environmental quenching. A galaxy falling into a dense cluster environment encounters the hot intracluster medium, which acts like a headwind, stripping cold gas from the galaxy through a process called ram pressure stripping. Without cold gas, the galaxy cannot form new stars. It fades, reddens, and becomes quiescent. Finding quiescent galaxies in a protocluster at a redshift of 3.44 implies that environmental quenching was already operating when the universe was less than 15% of its current age. The dense environment of the vine was already influencing its member galaxies, shutting down star formation in some of them before the structure had even finished assembling. Galaxies in the vine were not merely clustering together, they were already changing each other. The vine also illustrated something important about the geometry of early structure. It does not look like a galaxy cluster. It looks like a segment of the cosmic web, a filament caught in the act of feeding matter into future cluster cores. This is precisely what simulations predict protoclusters should look like at intermediate redshifts. They are not spherical concentrations but elongated, filamentary structures stretching across tens of megaparsecs, channeling gas and dark matter toward the densest nodes. The vine confirmed that Webb could not only find early galaxies, but could trace the underlying cosmic web architecture at epochs previously inaccessible to observation. These were not isolated discoveries. Across multiple survey fields, Webb was identifying galaxy overdensities at redshifts above 5, 6, and 7. A protocluster candidate at a redshift of 7.66 was identified behind the lensing cluster, known as SMACS 0723. Overdensities of Lyman alpha emitting galaxies at a redshift of approximately 7 were found in the Leger survey fields, and the results from those fields illustrate a dimension of the protocluster story that goes beyond mere galaxy counting. When the team obtained Webb and Keck spectroscopy of galaxies in the Leger overdensity, they found that the structure contained 3 distinct subclusters, each one a concentration of Lyman alpha emitting galaxies surrounded by its own ionized bubble. These bubbles, regions of space where hydrogen had been ionized by the ultraviolet radiation from the member galaxies, were approaching the point of overlap. The ionized zones created by each subcluster were reaching toward one another across the surrounding neutral intergalactic medium, creating a patchwork of ionized and neutral gas that mapped the protocluster's gravitational geography. This finding reveals something profound about the relationship between early structure and cosmic reionization. Protoclusters did not merely form within the reionizing universe, they actively shaped the reionization process. A concentration of galaxies in one region produces far more ionizing radiation than the same number of galaxies scattered randomly across space. The combined ultraviolet output of a protocluster can carve large ionized bubbles in the surrounding neutral hydrogen, creating regions where reionization completes earlier than the cosmic average. This means that the densest regions of the early universe, the places where protoclusters were assembling, were also the first places to become transparent to ultraviolet light. Structure formation and reionization were not independent processes. They were coupled, with the earliest structures driving the earliest chapters of the universe's transition from opaque to transparent. In the JWST survey fields themselves, systematic searches identified multiple protocluster candidates in the redshift range of 5 to 7, each characterized by an excess of galaxies concentrated in volumes far smaller than random chance would predict. A recent comprehensive study cataloguing all known massive galaxy overdensities during the reionization era found that these structures appear to be deeply embedded in gas-rich, partially neutral environments of the cosmic web, with properties suggesting they trace sites of enhanced gas supply rather than uniformly accelerated galaxy growth. A pattern was forming. The early universe was not merely producing individual galaxies ahead of schedule, it was producing the environments in which galaxies gather. The filaments, the overdensities, the nodes of the cosmic web were already taking shape within the first billion years. Structure was not waiting for the slow, patient timeline that lambda-cold dark matter simulations had laid out. It was assembling faster. The scaffolding was going up sooner. But there was a persistent question hovering over every one of these discoveries, a question that separated tantalizing hints from definitive proof. Finding an overdensity of galaxies at the same redshift is compelling evidence for a protocluster, but it is not conclusive. Galaxies can cluster along the line of sight due to large-scale filamentary structure without being physically associated in a single collapsing system. Photometric redshifts carry uncertainties that can scatter unrelated galaxies into apparent overdensities. Even spectroscopic confirmations, while far more reliable, show only that galaxies occupy the same narrow slice of cosmic time, not necessarily that they are gravitationally interacting. A collection of galaxies at the same redshift might be a genuine protocluster, or it might be a chance superposition of objects within a broader filament, a structure that will never collapse into a single cluster. To move from candidate to confirmation, astronomers need additional evidence. Ideally, they need to see not just the galaxies themselves, but the medium between them. In a mature galaxy cluster, gravity has pulled gas inward from the surrounding cosmic web for billions of years. As this gas falls into the cluster's deep gravitational potential, it is compressed and heated by shock waves to temperatures of tens of millions of degrees. At these temperatures, the gas becomes a fully ionized plasma that radiates powerfully in X-ray wavelengths. This hot intracluster medium is the defining physical characteristic of a galaxy cluster. It is what separates a true cluster from a loose association of galaxies that happen to be near each other. The intracluster medium represents the thermodynamic evidence that gravitational collapse has proceeded far enough for the cluster's potential to heat in falling matter to extreme temperatures. In a protocluster, This gas should be in its earliest stages of heating. The potential well is still growing. The gas is still falling inward. The temperatures may not yet have reached the levels seen in mature clusters, but if the protocluster is massive enough and has been assembling long enough, the earliest traces of a heated intracluster medium should be detectable, a faint glow of X-ray emission marking the moment when gravitational collapse transitions from a collection of galaxies sharing a neighborhood to a genuine structure building a shared atmosphere. Before 2026, no protocluster at a redshift above 5 had shown this signature. The Abell 2744 protocluster at a redshift of 7.88 had galaxies, but no detected hot gas. The cosmic vine at a redshift of 3.44 was a filamentary structure, not a concentrated collapse with a unified gas atmosphere. Every other high redshift protocluster candidate identified by Webb shared the same limitation. They showed galaxy overdensities, sometimes dramatic ones, but the gas between those galaxies remained invisible to X-ray telescopes. Without the gas, the case for genuine cluster formation remained circumstantial. The galaxies were gathering, but the evidence that they were building something truly massive, something with the gravitational depth to heat baryons to millions of degrees, was missing. The significance of this missing signature cannot be overstated. Galaxy overdensities are interesting. Hot intracluster gas is transformative. Finding galaxies clustered together at a redshift of 6 is a statement about local density in one small region of the cosmic web. Finding hot gas at a redshift of 6 is a statement about the entire history of gravitational collapse in that region, because producing that gas requires a gravitational potential well deep enough and old enough to have accumulated and shock-heated a substantial reservoir of baryonic matter. It is the difference between finding a group of people standing near each other on a construction site and finding the foundation of a building already poured beneath their feet. One suggests intent. The other proves that construction is underway. The previous record holder for a protocluster with detected X-ray emission existed roughly 3 billion years after the Big Bang. That was the earliest epoch at which astronomers had observed the hot gas signature that indicates a cluster is genuinely forming. Everything earlier had been galaxy overdensities only, suggestive but incomplete. And then, in January 2026, 2 observatories looking at the same patch of ancient sky, one seeing infrared light and the other seeing X-rays, announced a discovery that pushed that record back by roughly 2 billion years. The galaxies had been found, the gas had been found, and both existed at a cosmic epoch when most models predicted neither should be there. What came next would force the astronomical community to confront a timeline problem far more severe than early galaxies alone had created. To understand what was found in the Chandra deep field south, you first need to understand the instrument that found it. X-rays cannot be observed from the ground. Earth's atmosphere absorbs X-ray radiation completely, which is fortunate for life on the surface, because X-rays carry enough energy to damage biological molecules, but deeply inconvenient for astronomers who want to study the hottest, most energetic phenomena in the universe. Every X-ray telescope ever built has had to operate in space, and building a telescope that focuses X-rays is itself a formidable engineering challenge, because X-rays do not behave like visible light when they encounter a mirror. A conventional telescope mirror, the kind used by Hubble or Webb, reflects light that hits its surface at steep angles. X-rays, however, pass straight through most materials rather than reflecting. The only way to redirect them is through grazing incidents, bouncing them off a surface at an extremely shallow angle, the way a stone skips across water. Chandra's mirrors are not the familiar dish shape of an optical telescope. They are nested cylinders of precisely polished glass, arranged so that incoming X-rays strike the inner surface at angles of less than 1 degree, gently curving their paths toward a focal point nearly 10 meters away. NASA's Chandra X-ray Observatory launched in July 1999 aboard the Space Shuttle Columbia. It was deployed into a highly elliptical orbit that carries it more than a third of the way to the Moon at its most distant point, far above the radiation belts that would otherwise contaminate its sensitive detectors. For more than 25 years, Chandra has been the sharpest X-ray eye humanity possesses. Its angular resolution, roughly half an arc-second, remains unmatched by any other X-ray telescope. This resolution allows Chandra to distinguish individual X-ray sources that are separated by tiny angles on the sky. a capability essential for studying crowded fields where multiple sources overlap. It was this instrument, patient, precise, and uniquely capable, that stared at one particular patch of sky for longer than any other X-ray observation in history. The Chandra Deep Field South is one of the most studied patches of sky in the history of astronomy. Located in the southern constellation Fornax, this unremarkable-looking region spans an area on the sky roughly the size of a grain of rice held at arm's length. There are no bright stars in the foreground to contaminate observations, no nearby galaxies to overwhelm faint background sources. It is, by deliberate selection, the most boring patch of sky imaginable, and that is exactly why it became one of the most important. Over more than 2 decades, Chandra accumulated approximately 7 million seconds of exposure time on this field. 7 million seconds is roughly 80 days of continuous observation, spread across numerous campaigns stretching from the early 2000s through the 2020s. The result is the deepest X-ray image ever taken of any region of the sky. To understand the depth of this image, consider what depth means in astronomical terms. Every telescope has a sensitivity threshold. Below that threshold, sources are too faint to detect above the noise inherent in the instrument and the background sky. Increasing exposure time lowers that threshold because more photons arrive and the signal accumulates while the noise grows only as the square root of the time. This extraordinary depth of exposure allows Chandra to detect X-ray sources so faint that they emit only a handful of photons per year in the direction of the telescope. These are sources that would be completely invisible in an observation lasting hours, days, or even months. Only a commitment, measured in years of cumulative exposure, could reveal them. Every photon of X-ray light arriving from this tiny patch of cosmos was collected, catalogued, and analyzed. The image reveals hundreds of faint X-ray sources, many of them active galactic nuclei where supermassive black holes devour surrounding matter and radiate tremendous energy. Others are distant galaxy clusters, their hot intracluster gas glowing faintly across billions of light-years. A few sources remain unexplained, their nature uncertain because they are so faint and so distant that even the deepest observations provide only minimal information. The depth of this image means that even extremely faint X-ray signals that no other observation could detect, become visible if they exist. The same patch of sky also happens to overlap with one of the premier survey regions of the James Webb Space Telescope, the JWST Advanced Deep Extragalactic Survey. Known as JADES, is one of Webb's largest and deepest guaranteed time observation programs. JADES used more than a month of Webb's observing time to image the Chandra Deep Field South and the adjacent Great Observatory's Origins deep survey fields in multiple infrared filters, reaching depth sufficient to detect galaxies at the faintest luminosities and highest redshifts. The survey also obtained extensive spectroscopy with Webb's near-infrared spectrograph, measuring precise redshifts and chemical compositions for thousands of distant galaxies. JADES is not a survey designed to find one specific object. It is a census, a systematic accounting of the galaxy population across cosmic time, pushing deeper and further than any infrared survey before it. The overlap between the deepest X-ray image ever taken and one of the deepest infrared surveys ever conducted created a unique opportunity that exists nowhere else in the sky. Other survey fields have deep Webb data, but shallower X-ray coverage. Other fields have moderate X-ray depth, but less comprehensive infrared spectroscopy. Only in the Chandra Deep Field South do the two most powerful windows on the high redshift universe, infrared and X-ray, coincide at their respective maximum depths. For the first time, astronomers could examine the same volume of the early universe in two fundamentally different kinds of light. Infrared light reveals galaxies, their stars, their gas, their chemical compositions, their distances. X-ray light reveals something else entirely. It reveals superheated plasma, gas, heated to millions of degrees by gravitational processes, so violent that the atoms are stripped of their electrons and radiate at the shortest wavelengths the electromagnetic spectrum can produce. Think of it as the difference between counting the people who live on a street and measuring the temperature of the ground beneath their houses. The first tells you who is there. The second tells you whether something massive and hot is buried underneath, something too deep and too powerful to see with ordinary eyes. In a study published in January 2026 in the journal Nature, a team led by Arkosh Bogdan of the Center for Astrophysics at Harvard and the Smithsonian, along with collaborators Gerrit Schellenberger at the same institution and Chong Li and Christopher Consolis at the University of Manchester, combined these two extraordinary datasets and found something that most models predicted should not exist. The discovery began with the infrared data. An earlier study led by Chong Li had systematically searched the JWST field for protocluster candidates by identifying overdensities of galaxies at matching redshifts. The search covered the redshift range from approximately 5 to 7, corresponding to the first billion years of cosmic history. 6 protocluster candidates were identified. Among them, one stood out. Not because it was at the highest redshift, but because it contained more galaxies, packed more densely, within a more concentrated volume than any other candidate in the field. Its galaxy richness and inferred halo mass were the highest of the 6 candidates, placing it in a class by itself within the JWST survey volume. JWST ID. One sits at a redshift of approximately 5.68. In terms of cosmic time, this means the light from this structure was emitted roughly 1 billion years after the Big Bang. The universe at that moment was approximately 7% of its current age. Stars and galaxies had been forming for several 100 million years, but the cosmos was still a young and comparatively sparse environment. The epoch of reionization, the period during which ultraviolet radiation from early stars and galaxies gradually ionized the neutral hydrogen filling intergalactic space, was still underway. Large-scale structure was in its earliest stages of assembly. Within this early environment, Webb identified an extraordinary concentration of galaxies. At least 66 individual galaxies were flagged as potential members of JWST. ID1, all located at consistent redshifts within a relatively compact region of sky. The overdensity was quantified statistically. The probability of finding this many galaxies at this redshift within this volume by random chance was calculated at roughly 1 in 70,000, corresponding to an approximately 4.2 sigma detection. This is not marginal. In statistical terms, 4 sigma sits well above the threshold for a confident detection, though below the 5 sigma standard often cited in particle physics for a definitive discovery. The researchers also verified that no other substantial galaxy concentration existed at lower redshifts along the same line of sight, ruling out the possibility that a foreground structure was contaminating the overdensity measurement. The galaxy overdensity alone made JWST 1D most compelling protocluster candidate in the JWST field. But what made JWST ID unique among all high redshift protocluster candidates was not the galaxies, it was what lay between them. When the team turned to the deep Chandra X-ray data covering the same region, they were not necessarily expecting a detection. The history of high redshift protocluster searches in X-rays is a history of non-detections. Every protocluster candidate above a redshift of 5 that had been checked for X-ray emission had come back empty. The universe at those epochs was thought to be too young, the potential wells too shallow, the gas too diffuse for any detectable X-ray signal. Even in the deepest X-ray image ever taken, the expectation was silence. The Chandra data for the JWST ID1 region could have shown nothing, and nobody would have been surprised. That outcome would have been consistent with every prior result and every theoretical prediction. Instead, the data showed something. Extended X-ray emission coincided with the galaxy overdensity. Not a point source, which would indicate a single active galactic nucleus or a lone accreting black hole, but a diffuse glow spread across the same spatial extent as the galaxy concentration. The signal was faint. It was unmistakably there. The distinction between point source and extended emission is critical and required careful analysis. Active galactic nuclei produce intense X-ray emission, but it comes from a compact region surrounding a single supermassive black hole. The emission from JWST ID1 was spread over a much larger area, consistent with hot gas filling the volume between the member galaxies, rather than radiation from any single object within the structure. The team performed detailed spatial analysis to confirm that the signal could not be attributed to one or more unresolved point sources blended together by the telescope's angular resolution. They also verified that the signal's spatial profile matched the expected emission pattern from a hot gas atmosphere, rather than the sharper profile of a point source convolved with the telescope's optics. This is the signature of the intracluster medium. Gas falling into the gravitational potential well of a massive dark matter halo, compressed and heated by accretion shocks, reaching temperatures that can exceed 10 million degrees and emitting X-rays through thermal braking radiation produced when charged particles are decelerated by interactions with ions in the plasma. To grasp the significance of this detection, consider what it replaced. Before this result, the earliest known protocluster with detected X-ray emission existed roughly 3 billion years after the Big Bang. 3 billion years is a substantial fraction of cosmic history. By that epoch, the universe had already undergone more than 20% of its total evolution. Star formation had been underway for billions of years. Massive galaxy clusters were well into their assembly process. The cosmic web was mature enough that its largest nodes had developed deep gravitational potential wells capable of heating gas to the temperatures required for X-ray emission. Finding hot gas at 3 billion years was not shocking. It was expected. JWST ID1 pushed that record back to 1 billion years. The gap between the previous record and this new detection is not incremental. It is a leap of 2 billion years. To understand what 2 billion years of cosmic evolution actually contains, consider what happened between the universe's 1 billionth birthday and its 3 billionth. During that interval, the cosmos underwent some of the most transformative changes in its entire history. The rate of star formation across the universe climbed steadily upward, approaching the all-time cosmic peak that would occur roughly 3.5 billion years after the Big Bang. Galaxies that had been small, irregular, and chaotic during the first billion years grew through relentless mergers into the recognizable structures that populate the universe today. The Milky Way's own disk was beginning to take shape during this period, its earliest stars forming in a halo that would gradually flatten and organize into spiral arms over the billions of years that followed. Across the cosmos, billions of galaxies were assembling through hierarchical merging, each collision combining stellar populations, mixing gas reservoirs, and deepening gravitational potential wells. The cosmic web itself was maturing. During the first billion years, the web existed as a faint sketch, a network of modest overdensities connected by tenuous filaments of dark matter and gas. By 3 billion years, the web had sharpened into the robust architecture that cosmologists observe in the nearby universe, with well-defined filaments, dense nodes, and evacuated voids. Massive galaxy clusters were well into their assembly during this period, accumulating hundreds and eventually thousands of member galaxies, pulling gas inward from surrounding filaments, heating that gas through accretion shocks to tens of millions of degrees, and producing the X-ray bright intracluster atmospheres that make clusters visible to observatories like Chandra. All of that evolution, all of that structural development, all of that gravitational deepening and gas heating is what was supposed to fill the gap between 1 billion years and 3 billion years. That is the gap JWST ID1 leapt across. The previous X-ray record sat comfortably within that mature, well-developed cosmic era, an era when clusters had already been forming for over 1 billion years, when the cosmic web was robust, when the conditions for producing hot intracluster gas were well established. JWST ID1 sits before all of it, at an epoch when none of that development had yet occurred, when the universe was still raw and sparse and barely past its first generation of substantial galaxies. 2 billion years of hierarchical merging, of halo assembly, of gas accretion and shock heating, that JWST the first D1 appears to have compressed into a fraction of the time anyone predicted. The measured X-ray luminosity of JWST 1D1 was approximately 1.5 times 10 to the 44th power ergs per second. This is a faint signal by the standards of nearby galaxy clusters, which typically produce X-ray luminosities tens or hundreds of times greater. But it is enormous by the standards of the early universe, where no comparable signal had ever been detected at such a high redshift. From the X-ray luminosity, the team inferred the total gravitating mass of the system using scaling relations that connect X-ray properties to halo mass. These relations are well calibrated for nearby galaxy clusters and have been extended to higher redshifts with theoretical corrections for the evolving relationship between gas properties and total mass. The result was a total mass of approximately 1.8 times 10 to the 13th power solar masses, or roughly 20 trillion times the mass of our Sun. To place this number in context, the Milky Way's total mass, including its dark matter halo, is roughly 1 to 2 trillion solar masses. JWST ID. One is approximately 10 to 20 times more massive than our entire galaxy, including all of its invisible dark matter, and it exists at a cosmic epoch when structures of this mass were supposed to be extraordinarily rare or non-existent. This places JADE's ID1 in the mass range of a progenitor of today's most massive galaxy clusters. It is not yet a mature cluster. Its mass is well below the quadrillion solar mass scale of the richest nearby clusters, but it is already far too massive to be a single galaxy or even a typical galaxy group. It is a structure, a genuine concentration of dark matter, baryonic gas, and dozens of galaxies undergoing gravitational collapse on a scale that bridges the gap between the galaxy-scale objects Webb routinely discovers and the cluster-scale objects that Chandra observes in the nearby universe. The significance of detecting both signatures, the galaxy overdensity and the hot gas, in the same structure at this redshift cannot be separated from the history of protocluster detection. Every previous protocluster candidate at a redshift above 5 had been identified through galaxy overdensities alone. Webb had found collections of galaxies at matching redshifts in multiple survey fields. Some of these overdensities were dramatic, exceeding random expectations by factors of 10 or 20. But without X-ray confirmation, they remained candidates. The galaxies might be gravitationally associated, or they might be strung along a filament of the cosmic web, occupying the same narrow slice of redshift space, without being part of a single collapsing structure. The distinction matters because a filament is a feature of the large-scale density field, a highway along which matter flows, but it is not the destination. A protocluster is the destination, the node where filaments converge and matter accumulates into a bound collapsing system. The hot gas changes the interpretation fundamentally. Producing an extended atmosphere of X-ray-emitting plasma requires a gravitational potential well deep enough to trap infalling gas and shock heat it to extreme temperatures. This does not happen in filaments. It does not happen in loose associations of galaxies that merely share a redshift. It happens in structures where the dark matter halo has grown massive enough to dominate the local gravitational environment, where baryonic gas is being actively compressed by the weight of the surrounding matter, where the physics of cluster formation is genuinely underway. Detecting this gas at a redshift of 5.68 is direct evidence that JADE's the first D1 is not just a collection of galaxies in the same vicinity. It is a structure that has already begun the irreversible process of becoming one of the largest gravitationally bound objects in the universe. The team acknowledged important caveats in their analysis. The X-ray signal, while statistically significant, is faint. The Chandra Deep Field South provides the only survey volume in which such a signal could conceivably be detected at this redshift, because no other field combines comparable X-ray depth with matching infrared coverage from Webb. The scaling relations used to infer total mass from X-ray luminosity carry uncertainties, particularly at high redshift where the assumptions of self-similar evolution, the idea that clusters at all epochs follow the same relationships between mass, temperature, and luminosity, may not fully apply. If JADE's ID1 is experiencing mergers or major accretion events, its gas could be temporarily heated above the equilibrium temperature, inflating the inferred luminosity and mass. The team noted, however, that even merger-driven boosts introduce only modest biases in the scaling relations and do not qualitatively alter the conclusions. These caveats are standard in observational cosmology and do not undermine the core finding, but they mean the precise mass and luminosity should be treated as estimates rather than exact measurements. The 5 other protocluster candidates in the JADE's field sharpen the point. Each one represents a genuine galaxy overdensity at high redshift. Each was identified using the same methods and the same Webb data that revealed JADE's ID1, but none of them produced a detectable X-ray signal, even in the deepest X-ray exposure ever obtained. Their inferred halo masses were too low, their galaxy richness was too modest, their gravitational potential wells were too shallow to heat surrounding gas to X-ray-emitting temperatures. The Chandra data was deep enough, the structures simply were not massive enough. JADE's ID1 was not merely the best candidate among 6, it was the only one whose physical properties crossed the threshold required to leave a thermodynamic imprint visible from 12.7 billion light-years away. The other 5 candidates are real overdensities. They may eventually evolve into clusters, but at the epoch we observe them, Only JADES 1D CD1 had built enough gravitational architecture to announce itself in X-rays, setting JADES ID1 in context alongside other early protocluster detections sharpens its significance further. The protocluster behind Abell, 2744 at a redshift of 7.88, remains the highest redshift spectroscopically confirmed protocluster. Its 7 confirmed galaxies within 60 kiloparsecs represent an astonishing overdensity at an epoch just 650 million years after the Big Bang. But its inferred halo mass, roughly 4 times 10 to the 11th solar masses, is more than an order of magnitude below that of JADES 1D1. And critically, no X-ray emission was detected from this system. This does not mean the Abell 2744 protocluster is unreal. It almost certainly represents a genuine concentration of early galaxies within a dark matter overdensity. But its halo may not yet be massive enough to trap and heat sufficient gas for X-ray detection. It is an earlier, less evolved stage of the same process, a cluster seed rather than a cluster embryo. Its existence tells us that galaxies can find each other remarkably early. JADES ID1 tells us that the gravitational potential around those galaxies can deepen remarkably fast. The cosmic vine at a redshift of 3.44 represents a different kind of structure entirely, with 136 confirmed members stretched across 13 million light-years. It is a filamentary object, a segment of the cosmic web in the process of funneling matter toward dense nodes that will eventually become cluster cores. Its 4 identified subgroups suggest multiple collapsing regions within the broader filament. The 11 quiescent member galaxies indicate that environmental effects on galaxy evolution are already operating within the vine. But the vine is not a single collapsing object with a unified gravitational potential well. It is a landscape, a network of forming structures connected by a shared filament. Its redshift places it at a later epoch than JADES ID1, roughly 2 billion years after the Big Bang, making it less surprising from a timeline perspective even as its size and complexity remain impressive. Other protocluster candidates identified by Webb and ground-based facilities fill in the timeline at various redshifts. Overdensities at redshifts of 6.6 and 5.7 were identified before the Webb era using narrowband imaging surveys from facilities like the Subaru telescope, containing 12 and 44 galaxies respectively. Webb has since expanded the census dramatically, identifying candidates across the redshift range of 5 to 8 in multiple survey fields. But among all of these, only JADES ID1 showed the X-ray signature of heated intracluster gas. Only JADES ID1 met both criteria for a confirmed forming cluster, the galaxies and the gas. The statistical implications of the discovery extend beyond the object itself. The JADES field covers a relatively small area of sky. The survey volume at a redshift of approximately 5.7 is limited. Finding a structure as massive as JADES ID1 within this small volume implies either extraordinary luck or a higher abundance of such structures than standard models predict. The team noted this explicitly in their Nature paper, stating that the discovery of such a massive protocluster within the limited survey volume is statistically unlikely under standard lambda cold dark matter assumptions. The halo mass function, the theoretical prediction for how many halos of a given mass should exist at a given redshift in a given volume, assigns a very low probability to finding a halo of 10 to the 13th solar masses at a redshift of 5.7 in the volume surveyed by JADES. If JADES ID1 is a typical representative of the high-mass tail of the halo population at this redshift, then either the survey happened to sample an exceptionally rare region, or the halo mass function itself underestimates the abundance of massive halos at early times. This mirrors the broader pattern seen with early massive galaxies. Individual objects that are each improbable on their own become collectively difficult to dismiss when they appear repeatedly across independent survey fields. The publication of JADES ID1 in the journal Nature in January 2026 triggered immediate responses across the astronomical community. The result was described by the lead author as evidence that the universe was in a tremendous hurry to grow up. Coverage in Scientific American, the journal's own editorial commentary, and public communications from NASA and Chandra all emphasize the same point. This protocluster existed at a cosmic epoch when standard models predicted nothing of this scale should have been possible. But what exactly does that mean? How does one quantify the tension between observation and expectation? And what does this discovery, combined with the broader pattern of early galaxies and early overdensities, tell us about how the universe actually assembled its largest structures? The answer requires examining the specific predictions of lambda cold dark matter for structure formation in the first billion years and comparing them directly to what JWST, ID1, and its counterparts reveal. The tension is not a single number, but a compounding problem. Each new discovery at an unexpectedly early epoch does not merely add to a list, but multiplies the improbability, because each one probes a different aspect of the same underlying process. Early massive galaxies stress the model's predictions for star formation efficiency. Early protoclusters stress its predictions for halo assembly rates. Early hot gas stresses its predictions for the depth of gravitational potential wells and the thermal history of baryonic matter. These are not three separate problems. They are three faces of the same question. How quickly did gravity build organized structure in the first billion years? JWST, ID1, represents the sharpest version of this question yet posed. A single early galaxy can be explained by invoking unusual star formation conditions in one exceptional halo. A group of galaxies at the same redshift can be explained as a modest overdensity in the initial density field, a natural statistical outlier within the expected variance of lambda cold dark matter, but a structure with 66 potential member galaxies, a total mass of 20 trillion solar masses, and a heated atmosphere of X-ray-emitting gas, all existing 1 billion years after the Big Bang, occupies a different category of challenge entirely. This is not a challenge that can be addressed by adjusting the properties of individual galaxies. It is a challenge to the rate at which the large-scale density field itself evolved. The dark matter halo hosting JWST ID, one must have been assembling through mergers and accretion for a substantial period before the epoch at which we observe it, because producing a halo of this mass requires the convergence of many smaller halos, each of which had to form and grow through its own sequence of mergers. The gas within the halo must have been accumulating and heating for long enough to produce the observed X-ray signal, a process that requires time for infalling material to reach the temperatures necessary for thermal X-ray emission. The 66 galaxies within the structure must have formed from gas that cooled and collapsed within the halo's gravitational environment, a process that involves its own sequence of time-dependent steps. Gas accretion, cooling, fragmentation, star formation, chemical enrichment, every one of these processes takes time, and the universe at a redshift of 5.68 had only 1 billion years of time to give. The clock starts at the Big Bang. Subtract 380,000 years for the universe to cool enough for atoms to form and for the cosmic microwave background to be released. Subtract another 100 to 200 million years for the Dark Ages, during which the first dark matter halos were still growing through slow gravitational collapse. The first stars likely appeared somewhere between 100 and 250 million years after the Big Bang. The first small galaxies followed within a few hundred million years. That leaves a window of perhaps 500 to 700 million years for the dark matter halo hosting JWST ID1 to assemble from smaller halos, for its gas to begin accreting and heating, for 66 galaxies to form within its gravitational environment, and for the structure to reach a state mature enough to produce detectable X-ray emission. Standard lambda cold dark matter simulations, when run forward from the initial conditions observed in the cosmic microwave background, rarely produce halos this massive, this early. They rarely produce the galaxy overdensities observed at these redshifts, and they essentially never produce X-ray-emitting intracluster gas at redshifts above 5. The combination of all three in a single object, within a small survey volume, represents a genuine challenge to the standard timeline of structure formation. The paper is published. The data are public. The X-rays are real. The galaxies are confirmed. And the question that now confronts cosmology is not whether the early universe built structure faster than expected, but how much faster, and what that speed implies about the physics governing the growth of everything. Lambda cold dark matter is not a fragile theory. It is arguably the most successful quantitative model in the history of physical science applied to the universe as a whole. It predicts the temperature fluctuations of the cosmic microwave background to extraordinary precision. It explains the large-scale distribution of galaxies observed in surveys spanning billions of light-years. It accounts for the observed abundances of hydrogen, helium, and lithium produced in the first 3 minutes of cosmic history. It correctly predicts the statistical properties of the cosmic web, the distribution of galaxy clusters, the power spectrum of density fluctuations across a range of scales, spanning several orders of magnitude. When cosmologists describe lambda CDM as the standard model, they are not using that phrase casually. They are acknowledging that this framework has survived decades of increasingly precise tests and emerged, each time either confirmed or requiring only minor refinements rather than wholesale replacement. This context matters because it determines how scientists interpret discoveries like JADE's ID1, the discovery of a massive X-ray-emitting protocluster at a redshift of approximately 5.68, does not arrive in a vacuum. It arrives in the context of a model that works spectacularly well in almost every other domain. The tension is real, but the response to that tension must be proportionate to the strength of the evidence and honest about the difference between a model under pressure and a model that has collapsed. Lambda CDM has not collapsed. What it has done, progressively and undeniably over the past 3 years of Webb observations, is accumulate pressure in a specific regime. The first billion years of cosmic history. The predictions of the standard model for this epoch are clear and quantitative. Dark matter halos grow through hierarchical merging. The rate at which halos of a given mass appear at a given redshift is described by the halo mass function, a statistical distribution that can be calculated from first principles given the initial power spectrum of density fluctuations and the cosmological parameters measured from the cosmic microwave background. For halos massive enough to host galaxy clusters, the mass function predicts vanishingly small abundances at redshifts above 5. The probability of finding a halo with a mass of 10 to the 13th solar masses at a redshift of 5.7 within the survey volume of the JADES field is extremely low. Not zero, but low enough that finding one raises legitimate questions about whether the model's parameters or its underlying assumptions about how density fluctuations grow are precisely correct. The issue is not a single object. The issue is the pattern, JADES. ID1 is the most dramatic example because of its X-ray conformation, but it exists within a broader landscape of early structure that collectively applies pressure to the standard timeline. The protocluster behind Abell, 2744 at a redshift of 7.88. The overdensities identified at redshifts of 6 and 7 across multiple survey fields. The cosmic vine at a redshift of 3.44, with its already quenched member galaxies. The population of massive, luminous galaxies at redshifts above 10 that Webb has revealed across every deep survey. Each individual observation might be accommodated by invoking statistical fluctuations, rare peaks in the initial density field that happen to collapse faster than the average. But each invocation of rarity compounds the problem. If you need to invoke a 3 sigma fluctuation to explain one object, and a 4 sigma fluctuation to explain another, and both must occur within the same limited survey volume, the combined probability becomes increasingly difficult to reconcile, with a model that predicts these fluctuations should be independent and rare. Think of it as a river system where every tributary you measure turns out to carry more water than the watershed should allow. One unusually large tributary might be a local anomaly, a spring feeding extra flow into one branch. But if every tributary is oversized, the problem is not with any single branch. The problem is with your estimate of how much water the watershed produces. The density field in the early universe appears to have produced more structure, faster, across a wider range of scales than the standard initial conditions predict. Several classes of explanation have been proposed, and it is important to distinguish between them carefully. The most conservative explanations operate entirely within the existing framework of lambda CDM and seek to resolve the tension by adjusting astrophysical processes rather than fundamental physics. Perhaps star formation in the earliest galaxies was more efficient than at later epochs, driven by the absence of heavy elements and the resulting changes to gas cooling and fragmentation. Lower metallicity gas cools differently, potentially allowing a larger fraction of baryonic matter to collapse into stars within each halo. If early star formation efficiencies reach 30 or 40%, rather than the 5 to 10% typical of nearby galaxies, the observed luminosities and stellar masses could be reproduced without requiring more or larger dark matter halos than the model predicts. This approach can address the early galaxy problem but does not directly address the protocluster problem. Making individual galaxies brighter does not make halos more massive. It does not produce galaxy overdensities or X-ray-emitting gas. The protocluster challenge operates at a different level of the hierarchy, at the level of the density field itself rather than the baryonic physics within individual halos. A second class of explanations modifies the initial conditions. The power spectrum of density fluctuations measured from the cosmic microwave background describes the amplitude and distribution of those fluctuations across a wide range of spatial scales. The measurements are extraordinarily precise on large and intermediate scales, but on the smallest scales relevant to early galaxy and protocluster formation, the constraints become weaker. It is possible that the initial power spectrum contains slightly more power on small scales than current best-fit models assume. This additional small-scale power would seed more overdense regions in the early universe, producing more massive halos and more galaxy overdensities at high redshift. The effect would be strongest at the earliest epochs, exactly where the tension is observed, and would diminish at later times as structure formation on larger scales catches up. This explanation is physically motivated, technically viable, and testable, with improved measurements of the cosmic microwave background on small angular scales, and with observations of the abundance of early structures across wider survey areas. A third possibility involves modifications to the expansion history of the universe before recombination. Early dark energy is a hypothetical component that contributes additional energy density to the universe during the first few 100,000 years, briefly increasing the expansion rate before decaying away and leaving the late-time universe indistinguishable from standard lambda CDM. Early dark energy was originally proposed to address a different problem entirely: the Hubble tension, the persistent discrepancy between measurements of the cosmic expansion rate derived from the cosmic microwave background and those derived from local distance indicators like supernovae and Cepheid variable stars. But simulations have shown that early dark energy also accelerates early structure formation. By altering the expansion rate before recombination, it changes the relationship between the initial density fluctuations and the rate at which they grow, producing more massive halos at high redshift and easing the tension with observed galaxy populations. Recent large-scale hydrodynamic simulations incorporating early dark energy have produced galaxy luminosity functions and stellar mass functions in good agreement with Webb observations, without requiring additional calibrations beyond those used in standard simulations. Early dark energy is attractive because it potentially addresses two apparently unrelated problems: early structure formation and the Hubble tension, with a single modification. But it is far from confirmed. Its effects on the cosmic microwave background power spectrum are subtle, and current data cannot definitively distinguish between models with and without early dark energy. The next generation of cosmic microwave background experiments, including ground-based facilities with improved sensitivity to small-scale polarization patterns, will provide critical tests. A fourth possibility, more speculative but worth mentioning for completeness, involves modifications to the properties of dark matter itself. Standard lambda CDM assumes that dark matter is cold, meaning it moves slowly relative to the speed of light and clumps efficiently on small scales. But dark matter's true nature remains unknown. It has never been directly detected in a laboratory. Its properties are inferred entirely from gravitational effects. If dark matter has additional interactions beyond gravity, if it can self-interact, if it has a small but non-zero temperature, if it couples weakly to ordinary matter through forces not yet discovered, these properties could alter the rate and geometry of structure formation. Some models of warm dark matter, or self-interacting dark matter, produce different halo profiles and different assembly histories that might ease or worsen tensions with early structure observations, depending on the specific parameters chosen. These models carry their own constraints from other observations, particularly the cosmic microwave background and the distribution of matter on large scales, and none has achieved the predictive success of standard cold dark matter across the full range of cosmological tests. There is also a possibility that no single explanation suffices, and that the tension reflects a combination of factors. Slightly enhanced initial power on small scales, combined with more efficient early star formation, combined with environmental effects that accelerate galaxy assembly in the densest regions, could collectively produce the observed population of early galaxies and protoclusters without requiring any dramatic departure from the standard model. The universe is a complex system. Its behavior at any given epoch reflects the interplay of initial conditions, dark matter dynamics, gas physics, radiation, magnetic fields, and feedback processes operating across a vast range of scales. Attributing the entire early structure tension to a single cause may be an oversimplification. What is not an oversimplification is the observational record itself. The data from Webb, combined with Chandra's X-ray detection of hot gas in Jade's ID1, establish a set of facts that any successful model must reproduce. Fact 1. Galaxies with stellar masses exceeding 100 million solar masses exist at redshifts above 13, within 300 million years of the Big Bang. This is the discovery that started the current era of tension, the finding that the universe was already building substantial galaxies when the standard model expected barely more than the first faint proto-galactic seeds. Fact 2. Overdensities of galaxies at matching redshifts, with galaxy counts exceeding random expectations by factors of 10 to 100, exist at redshifts above 7, within the first 700 million years. These are not individual galaxies forming in isolation. They are collections of galaxies that have already found each other and begun congregating in the same gravitational neighborhoods, implying that the density field had already developed significant contrast on scales far larger than individual halos. Fact 3. At least one structure with a total mass of approximately 20 trillion solar masses, containing at least 66 potential member galaxies embedded in X-ray-emitting hot gas, exists at a redshift of approximately 5.7 within the first billion years. This is Jade's ID1, the centerpiece of this story, a structure that demonstrates not just that galaxies clustered early, but that the gravitational architecture hosting them had deepened enough to thermalize surrounding baryonic matter to temperatures of millions of degrees. Fact 4. The previous earliest detection of hot intracluster gas in a protocluster corresponded to an epoch roughly 3 billion years after the Big Bang, making Jade's ID1 approximately 2 billion years earlier than any comparable detection. This is not a marginal advance. It is a leap across a chasm in cosmic time, compressing 2 billion years of expected structural evolution into whatever accelerated process produced Jade's ID1's observed state. Fact 5. These observations come from small survey volumes, implying either extraordinary luck or a higher abundance of early structures than standard predictions. This is perhaps the most quietly devastating point of all, because it means the discoveries are likely not finished. If structures like Jade's ID1 exist in the tiny fraction of the sky that Webb and Chandra have surveyed at maximum depth, wider surveys may reveal many more, transforming what currently appears to be a rare anomaly into a systematic feature of the early universe. The abundance question is already being formally investigated. A study published in June 2026 directly confronted the question of whether there are too many protoclusters in the first billion years compared to lambda CDM predictions. The authors carefully compared the number of observed high redshift overdensities with the number predicted by cosmological simulations, and found that the answer depends sensitively on how protoclusters are defined and selected. Some observed overdensities may not evolve into present-day clusters at all, but instead represent extreme nodes of the cosmic web that will disperse over time. Others may be genuine progenitors of massive clusters that current simulations undercount because of limited volume or resolution. The study concluded that improved selection criteria, potentially incorporating total halo mass measured on Lagrangian scales rather than simple galaxy counts, are essential for making meaningful comparisons between observations and theory. But the underlying finding was clear. The abundance of early overdensities detected by Webb is high enough to challenge standard predictions and low enough that individual statistical explanations remain viable. The question is genuinely open, balanced on a knife edge between consistency and tension, exactly the kind of unresolved problem that drives science forward. These facts do not prove that lambda CDM is wrong. They prove that something about the first billion years was faster, more efficient, or more structured than the model's default predictions assume. The distinction matters. Declaring the standard model broken would be premature and scientifically irresponsible, given its extraordinary success across every other observational domain. But ignoring the accumulating tension would be equally irresponsible. The honest position, the position occupied by most working cosmologists as of 2026, is that the early universe is applying real and increasing pressure to the standard framework, and that the resolution will require either new astrophysics, new initial conditions, new pre-recombination physics, or some combination of all three. The next several years will be decisive. Multiple observational programs are specifically designed to test and refine the picture emerging from Webb and Chandra. Webb itself will continue observing. Deeper spectroscopic campaigns in the JWST field and other survey regions will identify additional protocluster candidates, measure the stellar populations and chemical compositions of their member galaxies, and determine whether JWST D1 is a singular anomaly or the most prominent example of a common phenomenon. Wider area surveys with Webb have already begun delivering results. The Cosmos Webb program, the largest contiguous Webb survey undertaken to date, has produced the most detailed three-dimensional map of the cosmic web ever made, tracing the network of galaxies, filaments, and voids all the way back to when the universe was 1 billion years old. Published in May 2026 by a team led by researchers at the University of California, Riverside, this map reveals the large-scale structure of the universe across nearly 14 billion years of cosmic history, with dense clusters and filaments glowing in bright concentrations and enormous voids stretching between them. The map is far more informative than earlier cosmic web reconstructions based on Hubble data alone, because Webb's infrared sensitivity detects galaxies at redshifts that Hubble could not reach, extending the Webb's mapped volume into the epoch where the tension with standard models is strongest. This is no longer a future promise. It is a delivered result, and its implications for protocluster abundance and large-scale structure statistics at high redshift are still being analysed. The Vera Rubin Observatory, expected to begin its legacy survey of space and time in the coming years, will map billions of galaxies across the southern sky, providing an unprecedented census of large-scale structure at moderate to high redshifts. While Rubin operates primarily at optical wavelengths and cannot reach the extreme redshifts where Webb excels, its enormous survey volume will constrain the abundance of massive clusters and protoclusters at redshifts of 1 to 3, filling in the evolutionary bridge between the early structures Webb reveals and the mature clusters observed in the nearby universe. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is designed to map the geometry of the universe by measuring the shapes and redshifts of billions of galaxies. Euclid's wide-field surveys will constrain the growth rate of cosmic structure across a broad range of redshifts, providing independent tests of whether structure formation proceeded faster than lambda CDM predicts. Its measurements of weak gravitational lensing will map the distribution of dark matter on large scales, testing whether the density field at intermediate redshifts is consistent with standard initial conditions or shows evidence for enhanced power on small scales. The Nancy Grace Roman Space Telescope, targeted for launch by 2027, will combine wide-field infrared imaging with spectroscopic capability, enabling surveys that bridge the gap between Webb's extraordinary depth in small fields and Rubin's enormous area at optical wavelengths. Roman will be uniquely suited to identifying protocluster candidates across wide areas at high redshift, providing the statistical samples that Webb's narrow survey fields cannot deliver. The synergy between Roman's wide-field discovery capability and Webb's deep follow-up spectroscopy will transform protocluster science in the late 2020s. On the X-ray side, future missions will determine whether JWST D1 is truly exceptional or merely the first of many early X-ray protoclusters waiting to be found. Current X-ray facilities are limited. Chandra's angular resolution is unmatched, but its collecting area restricts detections to only the deepest survey fields. The next generation of X-ray observatories, if approved and funded, will provide the combination of sensitivity, angular resolution, and survey speed needed to systematically search for hot gas in high redshift protoclusters across wide areas of sky. Until those facilities exist, JWST the first D1 will will remain the only confirmed X-ray-emitting protocluster in the first billion years, a singular data point whose broader significance depends on whether it represents a rare extreme or the tip of a much larger population. Ground-based facilities will contribute as well. The Atacama Large Millimeter Array can detect the thermal imprint of hot intracluster gas through the Sunyaev-Zeldovich effect, a distortion of the cosmic microwave background spectrum caused when microwave photons scatter off the energetic electrons in the intracluster medium. This effect is independent of redshift, meaning it can in principle detect massive clusters and protoclusters at any cosmic epoch. Targeted observations of known high redshift overdensities with the Atacama Large Millimeter Array could provide independent confirmation of hot gas in structures where Chandra lacks the sensitivity for direct X-ray detection. The theoretical response is equally active. Simulation groups are running new cosmological simulations with modified initial conditions, enhanced small-scale power, early dark energy, and alternative star formation prescriptions to determine which combinations of parameters can reproduce the full suite of early universe observations without violating constraints from the cosmic microwave background and large-scale structure at lower redshifts. The challenge is formidable. Any modification that enhances early structure formation must not overproduce structure at later epochs, where lambda CDM already provides an excellent fit to observations. The solution, whatever it turns out to be, must thread a narrow needle, producing more structure earlier while leaving the late universe unchanged. This is the shape of the problem as it stands in 2026. Not a crisis in the sense that the standard model has failed, not a revolution in the sense that a replacement has been identified, but a genuine, scientifically productive tension between observation and prediction in a specific regime, the first billion years, that demands explanation and will likely drive significant advances in our understanding of both cosmology and astrophysics over the coming decade. Step back and consider what the early universe has revealed through this sequence of discoveries. The first deep images from Webb showed galaxies that were too massive and too luminous for their epoch. The first systematic surveys showed those galaxies were not isolated, but gathered in overdensities that traced the emerging cosmic web. The combined power of Webb and Chandra showed that at least one of those overdensities had already grown massive enough to heat its surrounding gas to millions of degrees, producing the hallmark signature of a forming galaxy cluster at an epoch when no model predicted such a thing could exist. And the widest area Webb survey yet completed has now mapped the cosmic web itself back to 1 billion years after the Big Bang, revealing that the network of filaments, nodes, and voids that organizes all matter in the universe was already taking shape at the epoch when JWST the first D1 was assembling. Each step escalated the question. Finding an individual early galaxy asks how one halo formed stars so efficiently. Finding an overdensity of early galaxies asks how the density field developed so much contrast so quickly. Finding hot gas within that overdensity asks how gravitational collapse progressed far enough, fast enough, for the deepest potential wells to begin thermalizing their baryonic content within the first billion years. These are not three different questions. They are three measurements of the same underlying phenomenon, the speed at which gravity organized matter in the early universe. And that speed, by every measure now available, appears to have been faster than our cleanest, most precise, most thoroughly tested theoretical framework anticipated. This is not a comfortable conclusion. It does not fit neatly into a headline. It does not lend itself to declarations that physics is broken or that the Big Bang has been disproven. Those declarations are false. The Big Bang is confirmed by overwhelming evidence from multiple independent sources. Lambda-cold dark matter remains the most successful cosmological model ever constructed. What the data show is something subtler and, in its own way, more profound. They show that the universe's first billion years were more dynamic, more structured, and more architecturally ambitious than the model's default predictions assumed. The construction started earlier. The foundations were laid faster. The cosmic web began assembling its most massive nodes before the timeline allowed. Whether this means the initial conditions were slightly different from what we measured, or that dark energy played a role before recombination, or that star formation in the earliest halos operated under rules we have not yet captured in simulations, or that dark matter behaves in ways we have not yet discovered, remains genuinely unknown. The answer will come from the intersection of better observations and better theory, from wider surveys and deeper exposures, from more powerful simulations and more creative physical models. What will not come is a return to the comfortable picture that existed before Webb launched. The early universe has shown us something real. Galaxies forming in the first 300 million years, protoclusters assembling in the first 700 million years, hot intracluster gas appearing in the first billion years. The cosmic web was not a patient, gradual construction project proceeding on a predictable schedule. It was something faster, something more urgent, something that built organized architecture before the clock said it was allowed. The universe did not wait for our models to give it permission. It built its cities before we thought the first roads existed. And the most troubling, most fascinating, most scientifically productive question in cosmology today is simply this: how did it do that so fast?